we are starting organic chemistry, the last real segment of the year. I actually counted the November exam marks, and it worked out that out of the 100 marks on the exam, 66 of them we've already learned that content, which is 2/3, and 34 of them we still have yet to learn, which corresponds to the amount of units we have. We've done 4 units and we have 2 left. So we are right on the pathway to getting everything done. And as you all know, with those 66 marks that you've already learned, that puts every one of you in a passing territory for the end of year exam. So everything here that we learn is now gravy points that we're going to learn in organic chemistry. I know for organic chemistry, some of you it's your favorite, and some of you it's your least favorite. You already know what your feelings are about organic chemistry. So just know that we are going back to that. This first unit of organic chemistry is more emphasis on the analytical side. We're going to be looking more at like those graphs and how to determine what type of molecules we have and some reactions. The second half of organic chemistry that we do in unit 6, that half will be when it's heavy reaction time. We get our flashcards back. We could do some competitions in that second component. So with that being said, we're going to go over these standards like always, and then we'll jump straight into the lesson. So it looks like a lot. I do want to throw that out there. This looks like a lot of standards, but one of the things about the A-level curriculum is that a lot of the standards are kind of repetitive, meaning that even though this looks like a lot, there's really just a couple of ideas that we need to pull from here. And if you understand those couple of ideas, you're going to be just fine. How many of you remember polymers from last year? Do you remember the general idea of polymers? You might have forgotten it totally because it wasn't really featured on the AS exam at all, but it was a topic that we had went over. I guess we're going to need to review, right? The type of polymers we did last year are going to come back. Those type of polymers were called addition polymers. And then we're going to learn a new type of polymer this year called the condensation polymer. Do you need to get into the list?
My favorite is polymerisation now.
Okay. So what we're going to do is go over the 2 different types of polymers, addition and condensation. We're going to have to review condensation reactions because it's been a really long time since we've looked at that. Then we're going to be able to predict the type of polymerization. So we'll be going over that. And then finally, we're going to be looking at whether polymers can be degraded or not. So we're going to take a deep dive into why plastics don't decompose and then what alternatives we could use that would decompose. So just so you're aware. Review from AS Chemistry. In AS Chemistry, we learned about addition polymers. And the requirement for addition polymers is that your molecules have a double bond. So it has to be alkenes only. You should write that down. Alkenes only. And with an addition polymer, you may or may not remember that it's basically adding, welcome back. Good?
Yeah, we were both accepted.
You were both accepted?
Over there.
Congratulations. All right, so looking at here, the idea is that we are adding small molecules to each other over and over and over again. And so if you'll recall, this little n means what? It means many. And for polyethylene, it could be 10,000 or more, like the same over and over and over and over again. And so just as a review, we actually did this question in AS Chemistry, but just to review like how this structure goes. We have this C2F4 monomer. It's used to make PTFE, which is the lining in pans. So those nonstick pans, the lining's made of this. And so the first thing you want to do is state the type. Well, we only learned one type in AS, so it has to be addition. They're adding to each other. And then it's draw the repeat unit. So just remind reminder on how to do that. First thing you want to do is draw the Lewis structure in the display formula. So draw the Lewis structure. I know some of you will be able to do this in your head, but we should always go through the process. So draw the Lewis structure for C2F4. 2 carbons. How many fluorines? 4. So I would distribute them 2 to each carbon. Fluorine, 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 fluorine. Now, in drawing your Lewis structure, how many bonds must carbon have? Is the only thing that an organic chemist must know. 4. 4 bonds. So if you draw a carbon with a different amount than 4 bonds, just know that your whole paper is getting it, like that whole section is getting ignored. That's usually organic chemists like major like pet peeve is if you draw a carbon that has a different amount of bonds. Like the big idea. And so we've got this. That's PPFE. Then what we're doing is we have to draw the repeat unit. Do you remember what to do from there? Go ahead, Sabrina.
First, you have to out of the brackets first.
Okay, you can start that way, absolutely.
And then basically draw the structure without the double bond. And
Yep.
That's the double bond.
Yep.
And then you break things on both sides of C, just draw a line outside of the bracket.
Okay, so like that and that. And then you put a little
Like it's a little end.
here.
Do we not need to do like a -2 charge or something?
What?
Like a -2 charge or something?
Where would that charge be coming from?
I don't know, the other lines. Since both carbons should be missing a.
Okay, so just to be clear, no, there is no charge on this polymer. Why? Because what this means is that this is adding to itself. So just to like explain that a little bit more, it would be this, but this is just the peak. It keeps going. It's this, 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 and it just keeps going over and over and over again. So every carbon does have 4 bonds. Because every carbon does have 4 bonds, there won't be a charge. Like it has the correct amount of electrons. So these polymers, they will not have charges. Does that explain it? Okay. So then you put the little N here, basically that's the same thing repeating over and over and over again. All right. So this is what we did before. Now we're going to start getting to new information, like how can we twist it. So first thing is, this is actually a paper 4 question. And it's also with addition polymerization. And so it says, addition polymers can be classified into 2 groups. Either homopolymers, which they have to define for you because it's not part of the objectives. So this is a polymer made up of the same monomer unit over and over again. And a copolymer, which is a polymer made up of 2 or more different monomer units. And so here they're telling you that you have a copolymer, that you have one alkene that you are combining with a different alkene to make their addition polymer. And they ask you here, I don't think anything wrong, draw a length of this copolymer that contains 1 molecule of each monomer. So how would we prepare that, is the question. How would we prepare that? Like to visualize it for ourselves. How to visualize. How to visualize. Let's start with here. When you write your monomer units, you should always write them in such a way where you write your double bonds first, and then you write up and down what's connected to the carbon on each side. So it only matters what's connected to the carbon here and what's connected to the carbon here, because that's where you're going to get your expansion, is around the double bond. So here you're going to write CH3 at the top, and you're going to write H at the bottom. On the other carbon, you're going to have what? 2 H's plus this. What is this other one? We've got C, double bond C again. Here we've got an H, and it doesn't matter which one you put on the top or the bottom because there is free rotation around single bonds. So it doesn't matter if I had put the H on the bottom and the C6H5 on the top, or the C6H5 on the bottom and the H on the top. It doesn't matter. So then I put my C6H5 on the bottom. And some of you might be wondering, what is C6H5? Anybody know? That's benzene. That's literally this. That's what they're saying, that that's coming out. We have a whole chapter on benzene in the second half of organic chemistry, but just so you're aware, if you see that few hydrogens with that many carbons, it's C6H6 with benzene, and then losing one hydrogen means that the benzene is connected to something. And so this really is communicating, oh, that's benzene. We're just not writing benzene. And then over here, for the other carbon, so that's one carbon, and the other carbon has two hydrogens. And so the question is, how do we put these two together to make a polymer? What do you think? Any suggestions?
Remove the double bond and
Remove the double bond. So I usually just do it like this. Remove the double bond, and remember you extend them out, and then you just connect them to each other. So we would have C single bond CH3, single bond H, single bond CHH, and then here we're going to have CH, C6H5, and CHH. Good so far? Did you see how I just extended those lines? What does that mean? That means that it's going on and repeating over and over again, but each set has one of these and one of these that are combining. And then we write our little N. Yes, Isa.
Can we put better?
Can we put what? R. I've not seen that in a mark scheme. I don't think it's technically wrong, but the thing is, R just means the rest of the molecule. So I don't think it's technically wrong. I just haven't seen it in a mark scheme. So I can't tell you how stingy they would be with that. It's not technically wrong.
But it's not wrong.
Because it keeps going. But I would write the little S. And in most of the mark schemes for A level that I reviewed, they just write the brackets and the lines out and then expect you to know, yeah, that's gonna keep going over and over again. Now, what about the other way around? Look at the next question. An addition polymer made from two different alkene monomers is called a copolymer. A section of a polyalkene copolymer is shown. So this time they're giving you an already done polymer and a section of it. And they're asking you to figure out, hey, go backwards, think backwards. We gave you the product, go back and figure out what are the two monomers that make that. So what would you all be looking to do here? Go ahead, Sabrina.
Well, since we know that we combine them, basically we just do a double bond and see what this happens. I would skip every two carbons and then draw lines in between them, and then that basically tells you what the chemical is going to be. And then we just basically draw that like whatever.
You really got the right idea here. Awesome. You really remember this topic, Sabrina. Awesome. Okay, so you find a repeating pattern. And when I was looking at this last night, I saw the repeating pattern was CH3Cl, CHH. And then C2H5H, CH3H. And then here again, this is the same as this one right here is the same as that one right there. So really, they're showing you more than one of the chain, and they're asking you to figure out, okay, where are the different blocks at that we have to separate? And so it's here and here, because this is a repeat of what's over here. And so then all you have to do is then write this first block, the two carbons, like you said, and fold back in those lines to make the double bond. And so this would be CC, CH3, Cl, HH. And then over here, this would be CC, CH3, H, and then CH3, Cl. Does that make, or I looked at the wrong one. it would be the second one. This one. It would be C2H5, H, and then CH3H, like that. And then we put double bond there. Why don't we stretch out? Like, why don't we extend these out?
This monomer.
Because it's the bond, which means it's the one that makes the double bond, yes.
Why didn't you break that into sections of 3 carbons?
So this right here
Yeah.
doesn't repeat here. Like if you map it out, it's CH3Cl, then CHH. And then here, it's not that same pattern. Like it's not the same pattern. You have to find the repeating pattern. This doesn't repeat. Like if you break it off into blocks of 3, those are not repeating. Like they're not in the same order. So it can't be broken off that way. Make sense? Yes.
Monomer floating 3 carbons.
Doubt. Because it's always around, like wherever you're breaking it, it's always around 2 carbons and then you're breaking it out. Like the polymer is always around an alkene. So it's always going to be a 2 carbon repeat unit. Yes? Okay. So this is actually what we did before. We have done this in the past, addition polymerization. So now we're going to go on to the second type, which is called condensation polymerization. And so this is going to require us to remember a little bit about last year's organic chemistry reactions. We have to at least start introducing some of those reactions back because it'll help us understand what's going on. Before we start, what's condensation? Like in general, because usually you hear condensation and the first thing that has always come to my mind is like water droplets on a soda can or like a, a bottle. That's what I think of when I think of condensation, which is gas to liquid, right? And so condensation is actually the removal of water. And so in the change from gas to liquid, it would be the removal of water from the air to form water droplets on your bottle. So it's the removal of water from where it's at. And then in condensation reactions, you're always putting 2 groups together. So you're always putting 2 groups together by taking out water. Putting 2 molecules together by taking out water.
Would an acid-base reaction be a condensation?
Depends. You'd have to show me a specific instance.
Like NaOH and hydrochloric acid?
I don't think it would be classified that way because of the fact that those are ionic in nature and this is covalent in nature. So in those reactions, you're not actually breaking and forming new chemical bonds, but here you are breaking and forming new chemical bonds. So I think that's why those would not be classified. Why? Those are just classified acid-base. Which in the organic study, you also have acid-base reactions that go on. So in order for condensation polymerization to occur, you need to have specific functional groups that can react with each other. Specifically functional groups that have either OH on them or COOH on them. Something for global coming up?
Yeah.
Okay, so this can happen in one of 2 ways. The 2 different functional groups are found on the same molecule, or the 2 different functional groups are found on 2 different molecules. So this can happen in one of 2 ways. The 2 different functional groups are found on the same molecule, or the 2 different functional groups are found on different monomers. And I wrote a little note here that this always gives us small molecules as well. That small molecule could be water in most cases. However, it could also be HCl. So you should write that those are the small molecules that would be lost. Here, this is a very, 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 very important example of a condensation polymerization, one that we're going to learn about by next lesson. And just as a reminder, the next lesson is not Friday. That's your honor roll day. Your next lesson is on Tuesday of next week. So that's when we're going to continue Unit 5. Yes. Yeah, you can scan show code. You can't scan show code. Okay. All right, Joe.
Is my phone automatically sending me more?
While I'm waiting, does that mean that you all are going to that award ceremony to figure out like if with the Fleischer thing? Like, what does that
We
mean?
have to do an interview.
Oh, you have to do an-
And then get the awards.
Okay.
Okay. So, requirements. This is probably the most important slide of the entire lesson. Last time, I remember when I was revising the PowerPoint that I wanted to bring this in here. For an addition polymerization, you have to have a C double bond C in your monomer, and specifically the pi bond breaks. Meaning, if you'll recall, the first bond that holds your two atoms together is called the sigma bond. And the other bond is called the pi bond. The second and the third bond would both be called pi bonds. And so when you are making addition polymers, you only break that second bond. You don't break the first bond that holds the molecule together. That's what that statement is saying. And then for condensation reactions, you've got something different going on. You've got either OH or NH on one of your monomers, and you have COOH or COCl on the other. You're like, what is COCl? I'm sure. I'm about to tell you. So what does this mean? OH is alcohol. So when we mean OH, we're talking about alcohols, which means something like CH3OH, CH3CH2OH, so on and so forth, right? We have some sort of alcohol going on. What is NH? What does that mean? You have an amine. It specifically is amine. And so you've got something like CH3NH2. It's in the middle of the molecule. It's CH3NCH3H, like that. These are classified as amines. Amines only make 3 bonds. So OH means I've got an alcohol. NH means I've got an amine. So put a line here. So one of your monomers has to have either an alcohol or an amine. The other monomer has to have carboxylic acid or whatever COCl is, which is something you haven't learned before, but it's actually in the A-level curriculum. So I may as well tell you now. So COOH is carboxylic acid, and it's like this, right? You've got that going on. And what about COCl? What? That's something different. The Cl is taking the place of the OH. So it actually looks like this. It is called an acyl chloride. Acyl chloride. You should write that down. That's something that we have not went over before in the past. That is new vocabulary for us. There will be a whole set of reactions with acyl chlorides. They're actually more reactive than carboxylic acids. We'll learn that. They're more reactive than carboxylic acids, but they have to be prepped in a lab. Like they're not something that really usually naturally occurs. They're prepped in laboratory and used to make reactions more reactive. And so that would be this. COCl. That's acyl chloride. And so the idea of what happens in a condensation is you're going to lose the H from one of these. So you lose the hydrogen from these, lose the H from these. And here, you're either going to lose OH from a carboxylic acid, and from the acyl chloride, you're going to lose the chlorine. And then as you take those little groups away, you're going to combine your molecules. And if you forgot how to do this, I'm about to re-show you. You'll notice there's a blank slide coming up. I was thinking and I was like, they're not going to remember this. So we're going to go back over that process of condensation. So write this down. This is, like I said, this is probably the most important slide because this is the one that tells you how you're going to make your predictions. And remember all those standards I just showed you at the beginning? Most of them can be covered just by knowing this information and then knowing how to apply it.
Is that H3 or just?
Here it's H. This is just H, and here you're losing OH, and here that's just, and here you're losing Cl. All right, so let's see, how do we do that in application? Like, how would we do a condensation reaction? Before we do condensation polymers, which we're about to see, we need to know how to do a condensation reaction. And so polyesters and polyamines are two we're going to look at in a little bit. They're both called condensation polymers. And what you're doing, this is what I mean by take the H away from the alcohol. You're going to take the OH away, in this case, from the carboxylic acid. And then we're going to merge the two together to make an ester. This is just how we had a different name for it last year. We could have called it condensation, or we could have called it esterification. So we called this esterification, which is the process of making an ester. Called esterification. Just as a reminder, conditions. Oh boy. Conditions. This process is called heat under reflux. Remember that heat under reflux thing?
Danny, we did that
You
once.
boil it out, then you cool it back down, right? That's called the reflux process to synthesize exactly what you need. Yes.
I think what's it called? We did that once in a lab to determine whether it was like a carboxylic acid.
We did one organic lab. I'm working on some interesting ideas for organic labs for us. I'm about to place the chemical order for the year, and then whatever glassware we've broken, and I'll see if we can come up with something cool to do. But yeah, we have done an organic lab where we had to heat something to get the color change that we needed for a chemical test. We didn't do this stuff. However, it would be a cool one to do if we have the materials for it. I was talking to one of my college professor friends, and he was like, "Y'all could totally prepare esters. Like, we don't really, I have only one of these, and these are like $200 each. So I don't know that I could do that on a large scale, but, we'll see what we could do. Heat under reflux, that's this process. Condensers are expensive because this is a glass. This is glass, where it's a very specific glass that has water that goes on the outside, and then your chemicals go on the inside. So the water never actually touches the chemicals. It just basically is on the outside of the glass to pull the chemicals that are going through it back down. All right, so then there's a couple other notes here. The one is that you need concentrated sulfuric acid as a catalyst in this reaction. I should point that out, that this right here actually has concentrated H2SO4. Concentrated sulfuric acid, which is a little bit scary to work with. Okay, so this is the way that we had learned it last year. If I combine a carboxylic acid with an alcohol, I'm going to get an ester, and I'm going to take out water. And so just to remind us of that process, I have a blank slide coming up on the next slide to go over, like, what was that? Practice forming esters using condensation. So let's do first the display. Display. How would that look? So let me give you some reactants. C, H, 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 C, O, O, H plus. It's always a good idea to face your carboxylic acid and your alcohol towards each other. So when you're writing these reactions, it's easy to prepare them if you are writing them in the correct manner. That makes it easier to see. And so I'm going to pick that for my carboxylic acid, and I'm going to pick, I don't know, how spicy do I want to be? I won't be. We'll do secondary alcohol. Propanol. Okay, so that's the reactants. The line, concentrated H2SO4. And what was the condition? Heat of the reflux. Okay. And so what do we make? What's the process here? Condensation means take out what? Water. And so it's important to recognize that when we're taking out the water, we're taking out the H from here, and we're taking out the OH from here. The OH always comes from the carboxylic acid, and the H comes from the alcohol. That's how you remove the water. Luke, you missed the most important step. This was going over all the different variants of condensation, which basically you're going to always be removing your hydrogen either from alcohol or amine, and you're going to be removing your OH either from a carboxylic acid, or you're actually going to move a Cl from something called an acyl chloride. And so those are the two small molecules you could lose in the process.
Why does the OH come from the carboxylic acid when the carboxylic acid is the one that the acid?
It's interesting, isn't it? It's not an acid-base reaction. It's the simplest answer to that. It's not an acid-base reaction. It's a dehydration reaction. That's another way to call it, a dehydration, because you're removing water. And so you actually remove the H from the alcohol and the OH from the carboxylic acid, and then you get the carbonyl mixing with this to become an ester. And so our products would be in display formula, which is not my favorite, but important to understand because you can make sure the octet rule is satisfied when you are drawing. Go ahead, Sophia. You can scan, show, and go. COO. And then what goes with that? What goes next? What we see here. The C, CH, CH, and H. So that would be written in the structural format, and I want to put this here. Why am I writing that purple instead of red?
Bond between the two.
This is the new bond form. So that's the actual merging. And what's the additional product here?
H2O.
H2O. So that's the small molecule that's lost. All right, what about, because I'm not going to write everything in display. What if we wrote it in skeletal? What if we did something in skeletal instead? So, go ahead. Skeletal. What do we do now? What now? What are we taking out? What are we putting together? Take out OH from the carboxylic acid and take out H from the alcohol and merge everything else together, right? So then your product here would be you see it? And then the small molecule lost is? And do you want to see one in structural format?
No.
Do you need to see one in structural format?
No.
Like just as a reminder? Because, you know, there are 3 formats that exist, and although paper 1 is not a thing for A level, it does still exist. So what if I had, let's twist it up a little bit. Might be too simple.
I see structural, I'm writing in skeletal.
What?
If I see structural, I'm writing in skeletal. So
I think they're usually not as picky on the A level about that because they assume that you already know all 3 formats really well. I've seen it extremely infrequently in A level where they ask you for a specific format. Most of the answers are in skeletal in the mark schemes when you see them, and that's because we're going to work with a lot of and we don't write benzene in any other way typically, but skeletal is a large thing to write. So usually we just write most of our work in skeletal, and then in the skeletal form, you still have to write out your functional group characteristics. So those atoms still have to be written. Like Here I'm writing my alcohol clearly, and I'm writing my carboxylic acid clearly. But let's just take a look. So this would be, oh, I have to, gross. You still want to expand out, and that's one of the things. Even if we're doing structural, you still want to expand out around your functional group because that's how you know what's going to be merged. So I'm going to go ahead and just write this.
Wouldn't they write that as COOH?
That's what I'm saying. Even though if like you would write it as HO2C, when you're merging them together, it's not going to make sense. Like how do you separate which oxygen is rolling out? So even if we are writing our final answer in skeleton and structural, it is better to expand around your functional group when you're reasoning it out. So I always suggest expanding around the functional group, especially if it's part of the reaction. Because otherwise you may not recognize what you need to do. Same thing for polymerization. It's important to do the expansion with the Lewis structure so you understand how you're going to take a bond and stretch it out. Okay, so I get CH and then parentheses. Parentheses. CH3. 2. That's right. How that's good. So same thing. Concentrated H2SO4, heat under reflux. And if we needed to know the answer in structural, we would be putting still this, taking that out. And we would now write our answer as CH3, CH2. See if you recognize this. O2C. Oh. Yep. Because OOC, reading it left to right, O2C, and then CH3 too. Like just this would be the part that tells me. Yes. However, I will tell you as we get into polymerization, typically in the instructions from Cambridge, they will tell you to show clearly the new bonds that are being formed, which means that structural usually won't be the way that they're going to ask for it. They're usually going to want to see specifically this bond, the new bond that's being formed. So just FYI, but just a quick review. We did know these 3 formats at one time, and we should continue to be aware of them. All right, so that was regular making an ester from a carboxylic acid and then alcohol. So now what's the difference between that and a polyester? You're going to notice some things that are kind of informational in this lesson, kind of cool ideas. I will tell you if something's in the standards to memorize or if it's just a cool aside that you are being informed about. The standards have changed significantly in this section over the past several years, meaning that there were certain things that Cambridge used to make you memorize that they no longer make you memorize. So pay attention to the standards as printed in the beginning of the lesson, and that'll tell you exactly what you actually need to know. All right, so polyesters. Polyester formation requires something called a dicarboxylic acid. What does di mean? 2. A diol, 2 alcohols, or a monomer that contains a carboxylic acid and an alcohol. So either 2 carboxylic acids on the molecule, 2 alcohols on the molecule, or 1 carboxylic acid and 1 alcohol on the molecule. This is what you need to form something called a polyester. Have you heard the word polyester before? Like not in chemistry. Isn't that clothing? That's clothing. So this actual process that's being described here is the process of making polyester clothing, like those threads that you would use. And you're going to see a lot of interesting notes in this first section about things that relate to like real life and what people do and what people make. You'll see several of them in this lesson.
Like the tire?
Like the tire, yes.
They're gonna like tire. Wait, what's the tire?
Enhanced tires.
It was
We're gonna learn it in its entirety.
learn it tirelessly in its entirety. Entirely?
Oh, you're talking about Terraline?
No, tire.
No, tires. We're punning on tires about learning it tirelessly in its entirety entirely.
Got it. That sounds like a good wrap.
Until we're too tired.
Until we're too tired to continue. All right, so lactic acid. You might have heard of lactic acid before. That's actually if you your body naturally produces lactic acid. If you exercise and you get something called DOMS, which is delayed onset muscle strain, and if you've ever lifted weights the next day or you've done heavy exercise the next day, it burns. The burn is lactic acid. So the lactic acid that your body produces, it hurts, but it also shows that you're building muscle. So interesting side note, but the monomer here that we use is lactic acid that we can use for polyester PLA. And then there's benzene 1,4 dicarboxylic acid and ethane 1,2-diol that can be used as well. And so what do we mean by 1,4? The carboxylic acids are on carbon 1 and 4 of the benzene ring. They're far apart from each other. And then for 1,2-diol, it means carbon 1 has an alcohol and carbon 2 also has an alcohol. It has a name that you might have heard. If you look on any like Purell or sanitizer, you might have seen this product. It is called it's called ethylene glycol. That's its common name. I would not say that's based on hand
Yeah, but it's something hand sanitizer, that's the thick.
part of it. It's a thickener. Hand sanitizer has a bunch of stuff. It says it here. It should say it here. You've got water, isopropyl alcohol, caprylyl glycol, which is a similar product to the ethylene glycol, glycerin, tocopherol acetate, a cross-linked polymer of alkyl acrylate, propanol, and fragrance. I don't know what fragrance is. They don't want to say what that was. Some kind of chemical.
Fragrance.
It's just, I don't know the FDA standards, but whatever. Fragrance. All right. Which of these monomers form addition polymers and which, so this is our real first question, like real first, textbook. Which of these monomers are addition polymers and which are condensation polymers? What's that first one? What do we think? Condensation. It's condensation because you would be able to take out the H from the amine and you would be able to take out the OH from the carboxylic acid. So you could take out water, so it's going to be a condensation. It would form, if I put it again and again and again and again, it would form a condensation polymer, not an addition. What about the second one? That's addition. Because that's where you're breaking the double bond and just adding it to itself over and over and over again. NH2, CH2, COOH, what's that? Condensation. And the last one? Also condensation. So remember, for addition, you gotta have the double bond. For condensation, you've gotta have the groups that you remove to either get water or HCl.
Do we ever get that?
Actually, technically, if you think about it, elimination, taking something away, that's technically subtraction. However, I don't think they would accept you to write that in a Cambridge exam. Let's call that the addition-subtraction reaction. Okay. The table shows 3 pairs of monomers that are capable of polymerization. Complete the table by identifying each type of polymerization. So pair of monomers, type of polymerization. This is literally the same question, but this comes from a Cambridge exam. So paper 4. What type we got here? We've got condensation. Right? Second one. What's this? What's the second one? Condensation. Just instead of removing water, we're removing HCl. And then the third one. But they didn't show me the double one. Am I supposed to be able to know that myself? How did they even show it to me? Well, life is hard. If you display it yourself, you would see you would see with so many C's here that this carbon has a F, this carbon has a F. Oops, I have displayed this out. And if I had wrote everything here with a single bond, I should see a big problem in my life. What's that problem? This carbon right here with the amount of atoms drawn, that does not have 4 bonds. As drawn, that has 3 bonds. So what does Cambridge expect you to know? That that's a double bond. They didn't write it. They figured it out. I mean, you could just say that I don't see the OH in the Cl group. I don't see the, H in the OH groups. So it's not going to be the condensation. It has to be the other one. It's going to be anything. But if they gave you the option for it's neither, then you better check it out, right? So this one would be addition. The double bonds are there. They're just not written. Because at this level of understanding chemistry, they do expect that you can come up with it yourself. That you understand that because there are groups missing, carbon must have 4 bonds, so that must have 1 bond there. Okay, next. So now to the real type of major question you're going to see on the exam that has to do with this topic. Notice this last question, by the way, you had to get all 3 of those correct. You had 50-50 shot on each. Get all 3 of those correct. And it's worth how many marks? 1. Meaning if you got any single one of them wrong, you have 0 marks on this question. So does Cambridge consider this to be an easy question or a hard question? They consider this to be like simple, level 1. You just understand the basics. You can answer this question. So now, this is also 1 mark. How nice. You've been given fumaric acid. It can form addition and condensation polymers. How cool. It can do both. Why can it do both? Because it's got that double bond. So that gives you the potential for addition polymer. And it's got the double carboxylic acid. And remember, dicarboxylic acids can do condensation polymers if you mix them with something that has a OH or an NH. And so they're first asking us for 1 mark to draw the repeat unit of the addition polymer for it. So how would we prepare ourselves? I would prepare myself first to help visualize it. But if you can skip preparing and go straight to it, your brain does that, then you can do that. But I'm going to prepare how it needs to look for me to put it together. So how would I write this to make sense? How's it? Remember to identify your 2 carbons of the double bond. That's where you always have to begin with addition polymerization. So I would start by preparing by writing C double bond C. Then identify what are the 2 groups on that first carbon and what are the 2 groups on that second carbon. First carbon, I see H and CO2H. And here, for this one, CO2H on the top and H on the bottom. Now I want to go back to, let me see if I have that here. All the way back here. Here, you have free rotation, right? In a single bond. But here we do not. Do you agree? You do not have free rotation here. Why am I saying this? This is the trans variant. When you are creating your polymer, you actually have to, you should keep it trans to make sure that you understand this is the trans variant. So it should be written like this originally. Remember, once you write your product, it doesn't really matter. But if you did get a mark for like showing how it happens, then you'd want to know that that's trans, because these 2 groups are not going to be able to free rotate until they're in single bonds, if that makes sense. So once you make the polymer, then free rotation can happen. but at this point, it's in the trans configuration. Does that kind of make sense? All right, so then how do I get to my product here? Take that double bond, break it into 2 lines out, and then you get this. Now I know some of you are going to be like, wait, could I just write this in skeletal? How would that look like in skeletal? If I wanted to retain skeletal, how would this look? So that's a carbon. How would you do that? How would you do that skeletal? Yes. You can stand your own up. Remember for your carbons, you kind of have to like bend them. So there's your 2 carbons. And then you have a CO2H here and a CO2H there. You showed it very similar. So that would be skeletal. I don't like looking at the skeletal as much here. I think it's kind of weird. So I always switch mine to displayed, or like a displayed and structural mix that I think looks a lot easier to visualize. But if you wrote your answer like this, it's fine. Sometimes in the Cambridge Mark schemes, they'll also write their answer like that. Just so you're aware. Doesn't say we have to write our answer in a specific format here. So if it just says to draw it,
How would you write it in structural?
I don't think you can really write it well in structural because, I mean, I guess you would write it as, I've never seen them write it in structural to be clear, but I guess you would write it as CHCO2H, right? And then CHCO2H. Like that. That's even grosser. I actually hate that. I would never do. I mean, if you want to make me read that, okay. I do think this is the clearest way of presentation. The first one that I showed you. This you'll often see in mark schemes. Just know if you see it like this in mark schemes, as long as it doesn't say you have to do it in skeletal, which most of these don't tell you a specific format, you can write it whatever way your heart desires, as long as you make sure octet rule is satisfied and you're making sure that you're doing your connections at the right place. Okay. All right, so that was something that was addition polymer. So we're gonna go on to repeat unit for polyester.
I
So
already
this-
tried to write a 5-bond carbon on this one.
Yeah, me too.
I caught it, but you know.
I'm glad you caught it. Okay, so there is something you are going to have to understand in terms of how to write it properly. I know some of you have already started to work in advance of me, but I'm going to go ahead and write a preparation first so you can see the visualization of what happens. And then once you have the visualization of what happens, then you can just write the answer if you know how to do it in your head. But I'm going to help you visualize what happens. And so we need to put fumaric acid together with ethane-1,2-diol. So the first thing I wrote, so prepare. The first thing I wrote was fumaric acid. And I wrote it like this. HO-C-O-C-C-H-H. C-O-H. See if you're following me along. That's this written and displayed. Does that make sense? That's the fumaric acid. And I'm mixing that with ethane-1,2-diol. So I'm putting that together with H-O. I don't need to write this displayed, so I don't want to. C-H-H. CHH, because I want to make sure we are satisfying octet rule, so I'm fully displaying everything. All right, so this is the preparation. Then you've got to understand what happens. To make the polymer, we're taking the OH out from the carboxylic acid, and we're taking the H out from the alcohol. But we're doing this over and over and over again. So how do we show that here is the question. I'm going to change colors to show that. So, changing colors. OH and H. Take that out. Take that out. But we got to keep doing it welcome back. Again and again, which means on the outside, we also have to recognize that we're taking out the H from the OH and the OH from the carboxylic acid. So you should circle those groups. Put your little lines here. This is where the polymer is, right? And I wrote little notes here. Take out. Take out. Good so far? So how do we write that product? That's the question. If I'm going to start by writing from left to right. So I'm taking out the OH here. So the first thing I'm going to write is the single bond C double bond O. So then I'm going to write a little arrow here so you can see this is my answer. Okay, so C double bond O. Copy paste. C H double bond C H C double bond. Taking this out, 5. So what comes next after the C double bond O? So our eyes got to look over here to keep writing, right? So then O, C, H, H. You can see how large these are. And if you're not careful, you can get lost in the process real quick in terms of like what not to write and what to write. And all right. Cambridge accepts you to leave it like this. If you want to, you can write N here, saying that it's copied over and over and over again, but they accept it just like this. Yes? You see what I did? I took out the N's. Why did I take out the N's? Because it says that it keeps going over and over again. And then in the middle, I took out water, which formed that ester in the middle. Questions? It looks like a lot, right? You got to be very careful how you treat it. Do you want to see how they wrote it in the mark scheme? By the way, even though you can write it in this way, like I've shown you with all the bonds, however molecules are presented to you is how the answers will often be written in the mark scheme. So that means that because fumaric acid was presented like this, let's see from the mark scheme. So from the mark scheme, the same answer would be this is the mark scheme. Like that. Do you see it? Do you see it being the exact same thing? Would you pick one over the other? Personally, if I'm trying to understand chemistry, I would pick this. Once I'm an expert in octet rule, I would pick this. if I'm an expert in it. And do you need to show this part for a mark? You actually do not need to show this at all. The reason I'm showing this to you is to give you, understanding and clarity on how this even happens. If I just wrote this as the answer, you'd all be like, what? Yes. So that's a great question. One mark is for clearly showing the bonding here. That's where you link the two parts together. And the other mark is for the outside done correctly. With the little line there and the two lines going out at the right spot, like where the right atoms are connected. So that's where the 2 marks are awarded here. So there's no mark for doing this. All the marks are only in your final answer, which is why I said, if you can visualize it in your head, yes, you can jump straight to the final answer and be awarded full marks. But if you can't visualize it in your head, that's not a problem. Just draw everything out. One of my personal issues with organic chemistry when I was learning it is that I needed to do it this way. Like to understand what was going on. Why was that an issue? Because the tests are timed. So I would actually run out of time because I'd have to like visualize what's going on. And some people just had it in their brains that they could do it like this. And so that was one of the issues with organic chemistry for me in one of my classes, because the professor would give so many questions on a test that I'd be like, but I need to work it out. And I just wasn't able to work it out in time. And then later on, I learned find the professor that teaches a certain way so that it matches my learning style. And so I'd be like, oh, that teacher teaches that way. And I got an A in every other organic chemistry class after that. So just FYI, be careful. Same thing happened to me in calculus because I had to show on my substance. Like I would run out of time. Yes. You can scan to and go. All right, let's try another one. Maleic anhydride is an unsaturated cyclic compound used in the formation of several polymers. Very exciting. Maleic anhydride can be used. By the way, anhydride is that little unit there. They don't teach you that in Cambridge, but that is, if you were to take a full organic chemistry class, something you would be aware of. So then it's a cyclic compound used in the formation. It can be used to form maleic acid and tartaric acid. And then they say, this is what the one we care about. Maleic acid reacts with ethane 1,2-diol to form a condensation polymer. Draw a section showing only one. They bolded it, meaning if you do more than one, that's a no-no. And then the new functional group formed, go ahead, should be shown fully displayed. Meaning we don't care if you use skeletal or structural, whatever, for the rest of it, but wherever you make the new bond, you must display that. You must show that bond, meaning that the one that you make right here, that's the one that always has to be displayed, the one that puts the two together. All right, so let's see if we can do it. How do we prepare? How did I prepare earlier? I wrote out my maleic acid first, and I did write it out fully displayed. HO, COO. Then it's CH, COOH. And you may ask me, hey, Miss Lee, I see that this is in the cis configuration. Like that's cis, not trans. Is it okay that I've written it out like this?
Yeah.
Sure. First of all, because there's no mark for this. And second of all, because I'm just trying to show where my groups that are going to combine, where they're going to go. They're going to end up in a straight line at the end anyways. So may as well prepare them that way. And so this is fine. And then the 1,2 ethane diol or ethane 1,2 diol, that's going to be this. CHH, CHH, OL, or OH. And now what? How do we prepared it? How do we put it together? So that the group here comes out. And what else comes out?
H and OH conveyance.
The H has to come out from here, right? That H has to come out. Literally in your head, you could just erase it, right? And then on this side, what has to come out? The OH. And so if once you have that understanding, you can write the whole thing. So now it's going to be, our answer is, took the OH out. So we start with the C double bond O. C, H, C, H, C double bond O, O, C, H, H, C, H, H, and then O, there we go. And you put the little N on the outside. But even in these mark schemes, they don't require you write the N anymore. They're like, you got that. The lines on the outside going out is enough to say you have a polymer going on. And so 2 marks are awarded the same way. 1 mark is right there for showing that, and 1 mark is for the outside part at the correct atoms. That's how you earn the 2 marks. So what's the problem with this section on the actual paper 4? Because really this is, if you understand what's going on, it's not necessarily very complicated beyond the fact that the molecules are very large. The issue is because they are so large, first of all, it's easy to accidentally miss an atom or add 1 too many atoms. And if 1 atom is off, then the whole thing is wrong. They're like, hey, you're not obeying octet rule. We're ignoring the rest of this response. So that's one of the issues. And the second issue here tends to be what I had an issue with, which is the amount of time it takes to get it done. So because that's only 2 marks, and there's 2 marks for things that are way more simple, like knowing the the color of copper chloride, CuCl4. Well, not all marks are built the same. Remember, your strategy is to go for the easier marks first, and then go for the ones you know you can solve, and then for the ones that you're like, what is that they're even showing me? Maybe, hold off on those if you've got the time. You can go through them. And if you read them again at the end of the exam, you're like, I still have no idea what they're saying. And you did all the other stuff that you could. Don't stress yourself out. Continue. You're always going to see molecules, by the way, that you may never have seen before, but they give you enough information to solve the question from it. All right, we talked about polyesters in clothing, what it's used for, and so now we're going to talk a little bit about polyamides. And so first of all, from your cell work today, the amide group is one that you were not asked to memorize in AS chemistry because it's exclusively only discussed in A-level chemistry. So now, add it to your things to know. It's C-O-N. That's the amide group in chemistry. Con. You've got to see C-double-bond-O-N. Basically, it's almost just like an ester. Instead of C-O-O-C, it's C-O-N-C. So some people remember it as conch. Like there's conch shells. Some people remember it as conch because the next thing would be the R, would be the rest. It would be carbons. And so polyamides, just a little bit of history. This history is in the textbook. They were first synthesized by chemists in the 1930s. Nylon is one of the most interesting and important polyamides. If I'm able to get the right chemicals in my chemical order I'm going to place, one of the things we can do is we can make nylon. So we'll see. It's kind of cool because it has that like long stringy thing. Polyamides, they're made in the condensation polymerization reaction between a diamine, 2 amines, and a dicarboxylic acid or a dioyl chloride. You must be like, what is a dioyl chloride? That's fun. It's this. It's got a COCl and another DOCl. That's called a dioyl chloride. Yes. Diamines too, and then oil chlorides we're about to go over. They're acyl chlorides. How we name them is oil chlorides. They have a fun name. And so this is actually the reaction to make nylon 6,6. I pulled this from the textbook. You would take the water out, the H from the OH from the carboxylic acid. So very similar to what we've been doing with the alcohols and carboxylic acids. We're doing the same thing with amines and the carboxylic acids. And then this new bond that's here is what links the polymer together. It's called an amide link or the peptide link. That word peptide is on display next class and the class after probably. Anybody remember biology? It's been so long, maybe, unless you took those in Roman. It may have been recently. But there was something in biology called a peptide bond. And a peptide bond links amino acids together. We're going to learn that process next class. Like how amino acids link together, because it's literally the same process that's going on here. And it's actually one of the reasons that I say, if you understand the chemistry, biology actually becomes a lot easier. Because you'll understand the processes instead of memorizing what seems like random facts. So the chemistry behind it actually helps you understand what's going on at the higher level in biology. A couple of polyamides that are important. To be clear, this next section used to be tested and is no longer tested, but could still be used as examples if they provide you it. They used to just ask you straight up, what are the monomers for Kevlar? What is terylene? And so that was taken out of the standards in 2022. They're focused more on the actual just chemistry, understanding the chemistry now, instead of memorizing as many fun facts. But I did want to leave the fun facts in there because I think it's interesting to know. So Kevlar is a polyamide, and it is very strong. It is resistant to fire. So it's used in bulletproof vests, could be used by your firefighters to make their clothing, and the leather worn by motorcycle drivers. And it can be used also to strengthen tires. So that's called Kevlar. And what is the structure of Kevlar? Again, you do not need to memorize this anymore, but I did want to include it just because the textbook still talks about it, and I think it's interesting. So Kevlar has this structure. It is basically, this is a chain of the polymer, and this is another chain of the polymer. And the polymers stack on each other, and they are attracted to each other through something called hydrogen bonds, which makes their properties very strong because we're talking about thousands of these connections. So because we have thousands of these intermolecular forces of strong hydrogen bonding, it makes the material very, very strong. And these are the monomers that are used to prepare Kevlar. You can also use, this amine with that carboxylic acid, or you can use this amine with the acyl chloride, with the diboyl chloride, and that would give you this overall structure because it would repeat over and over and over again.
You should make Kevlar, Chuck.
You should make Kevlar. That's an interesting one. When I made this, I had not realized I already said this, but just to throw it out there, instead of diamino and dicarboxylic monomers, you can make synthetic polymers from monomers that are in the same molecule. Meaning, if you have a molecule that has an amino group and a carboxylic acid, you can just repeat that over and over and over again. And I wanted to show you an example of that. I think my last example has that. There's a couple of stuff. This is actually tested. So the other side notes about Kevlar, not tested, but this is tested. Meaning that you are responsible, and if you look back at the learning objectives from the beginning of the class, I mentioned biodegradation, right? Plastics are not biodegradable. If you remember, regular plastic, like our plastic bags that we get at the grocery store, are made of polyethylene. And polyethylene is the polyethylene is this. It's just carbons and hydrogens over and over and over again. This is not reactive. Why not? This does nothing. You could burn it. It actually gives you toxic chemicals that come out of it, but like this doesn't really react with anything. Why?
It's like really stable
It's
with,
super stable because it's non-polar, right? It's non-polar. There's no electronegativity, barely any electronegativity difference there. The bonds are really strong, not gonna break very easy. Literally, I said about alkanes when we first learned them, you could burn them. You can do free radical substitution, but that's it. You can't really do anything else with this thing. And that's why plastic is filling up our landfills. Why we have such big issues with plastic. And so what Cambridge wants you to know is that these condensates, so addition polymers are a problem. Addition polymers themselves are a problem because they're very stable and they are not very reactive. And so in recent years, there's been a big push to the production of biodegradable plastics and photodegradable plastics. And so for biodegradable plastics, these are made of condensation polymers. So plastics that instead of, taking ethene and mixing with ethene and ethene and ethene and adding, they mix different plant-based materials that have, because plants have those peptide bonds, that have the CONH or the CO bond. And so they have the amide or they have the ester bond. And those bonds can be hydrolyzed, meaning they can be broken apart. That will be a discussion for us next class because we're close to the end of this lesson. But we're going to talk about why these can be biodegraded better. It's because the bonds can be hydrolyzed. It means that those bonds can be broken at those areas, the amide bond and the ester bond. They also want you to be aware of photodegradable plastics. You don't have to memorize the idea. The only thing you have to know is that some plastics are photodegradable. You don't have to outline the process. You just have to say that's a possibility. And photodegradable plastics, they actually absorb UV light, which causes the bonds on the CO group to actually weaken the bonds, which makes it more reactive. And so it absorbs light, it vibrates, and then it becomes more reactive. But you have to have the C double bond O there. So the carbonyl group, like an aldehyde or a ketone. And then I did want to put this little side note in there. For those of you that are actively researching environmental science, There's some debate as to whether photodegradable plastics are actually better for the environment or not, because they have their own issues. And the next FYI, the reason I wrote FYI here is this is also no longer tested. But in the textbook, they put this as an aside. So if you have, I'll be putting this book up shortly. I have copied it to be able to put up on Google Classroom for you. But they put a nice long article about this topic in the textbook. That's really informative. I really liked it when I was reading it. So I don't usually like spend class time telling you to just read something. So we'll just go over it. And if you want to read more for context, it's in the textbook. And so there are actually polymers that can conduct electricity. And what they need is something called a conjugated, I don't know what, yeah, maybe. Pi bonding system. What does that mean? A conjugated pi bonding system is necessary for you to have a polymer that can conduct electricity. Meaning just like a metal, just like graphite, you can actually construct, as a chemist, a polymer that can conduct electricity. And what you would need to have is alternating double bonds on every other carbon. So that fancy wording means alternating double bonds on every other carbon.
Why does that make it conduct electricity?
So basically, all the pi bonding here. Here we go. Beautiful artistry, I know. All the pi bonding there allows for the movement of electrons throughout those pi bonds. You see it? Like electrons move through there. As long as the pi bonding system is conjugated. I can redraw that out. Do you want me to do that again?
Let's get just.
It's okay. I did the thing up and down, no? The electrons go through there. Electron movement means electricity. This isn't tested, by the way. But this is just how you know it happens. Yes. You can show and go. Yes. Means they can move through. It means they're not bound. So those pi bonding electrons, the sigma bonding electrons are bound, but the pi bonding electrons can move. So that's why you need the double bond, and it has to be every other. Because like if it wasn't every other, like let's say it was like this. You've got I'm doing my best, y'all. And the electron cannot go from there to there. It can't jump from there to there. They have to be every other. Do you see what I'm saying? Because it has to be able to flow through the pi bonding system. Okay, so why did Cambridge take the time to put the aside on this and this used to be tested? So these types of polymers are used for making plugs, electrical sockets, like switches. We talked about how we have this. Sometimes, and I read this, I thought it was really cool that they brought this up to you because you're not tested on this, but if you take any higher level chemistry or engineering or STEM, you'll learn this process. Sometimes they'll have other substances, iodine inserted into them, like the iodine atom, and it will improve their conductivity if you add other atoms in sometimes. This process is called doping. For those of you working on MOFs, you may want to research like doping because doping is that same idea that you can add in these different atoms to enhance properties. And so, yeah, it's
So dope.
it is so This actually gives the polymers that have these extra atoms in them some advantages over regular metal conductors, like your standard metals, your copper, your silver. And those specific enhanced properties include, well, it's not going to corrode. Metals corrode. Metals are reactive. Like these are alkene systems. They're not going to corrode over time. They're not going to be dissolved by acid. They're not going to react with acid. They're less dense. They're lighter in mass than the heavy metals. So low density. They can be formed into shapes easier. Think about how you shape plastic. Like you can bend it very easily. So it can be shaped very easily. And so they do get used, these electrically conductive polymers have been used in LED lights and flat panels, like flat panel TVs. When you would choose to use them as an engineer, if you were engineering a design, is if you want a lightweight material that conducts electricity, then you may consider, looking into one of these types of materials. So I think that that's a very interesting side note, especially since I know some of you do want to go into engineering, and the more knowledge base you have, the better. Yes.
So is that kind of like what's probably in our advertising?
Yes. Some of the LED screens. Okay, so are they going to test you on this? No. Is it interesting? Yes, I think so. I think it's interesting, and I think it's interesting that we can connect chemistry that we learn to something that applies, IRL, that in real life that people are actively working on. And that's actually what's really cool about the Cambridge curriculum is they do like to tie in a lot of, how does this apply? How does this apply? Where could we actually use this? I know we're looking at these really complicated, imagine missile disposal surface and be like, what? What is that? You all are probably still like, what? But, you got the idea. All right, so compound H has the structural formula of that. To a last practice question for the day. We haven't done anything with amines, so we need to do one. And I guess before we go for the day, before we finish this question, I'm going to say let's talk about homework. Homework is not going to be due on Friday. It's going to be due next week on Tuesday. And I'm going to trust that you're totally working on your homework on Friday, unless you're going to honor roll. Got it? But it's due on Tuesday, just so you're aware. And for those of you in honor roll, enjoy. All right, so compound H has the structure formula CH2, CH, CH, NH2, COOH. Polymers consist of monomers joined together by undergoing addition or condensation, polymerization. Compound H can react to form an addition polymer, K, or a condensation polymer, L. So draw one repeat unit of K. Why? They do this on your exam all the time. They're like, here are these random letters. Make it this random letter. They're literally just saying, hey, do addition polymerization with this. I don't know why it's gotta be worded. It's so weird. Do addition polymerization with that. How do we do that? Welcome back. Okay, so how do we do that? We look for the double bond, right? Double bond is addition polymerization. So we've got that C, double bond, hydrogen on the top and the bottom. And then what about this other carbon?
Yep.
Hydrogen on the top, maybe?
Yeah,
And then all that stuff on the bottom? I would just copy paste, like however this is written. I would just do the same thing so that you don't overcomplicate your life. If you try like mapping it out, you can, but are you wasting time? Yes. So just copy paste is easier. Okay, so that's preparation. So now what do we do? So like that, right? And if you're able to visualize that, you could just start. So then my answer, oh, and this is how many marks? 1 mark. And how many atoms am I writing for that 1 mark?
2.
Atoms? I'm writing a lot of atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9,
6,
10,
7?
11, 12, 13. Oh my God. Okay. And that, right? 1 mark. We're almost done. Ready for the last one? It says draw 2 repeat units. 2 repeat units of the condensation polymer L. So they're telling you H can be formed into L. I would start by, and what I did in my notes was I rewrote it out like at the top because I can't brain unless I have it right in front of me. So CH2 and then double bond CH, CH, NH2, COOH. Okay, so this one is, I would say, a little bit complicated because what are we supposed to be putting together for this condensation polymer? Like, just to help us understand, this is the H that's coming out, right? And what's the OH that's coming out? Okay, so how do we do that? First thing I suggest, draw two molecules. That's what they mean by two repeat units. It's the same molecule that's connecting. So draw two molecules. So I'm going to go ahead and draw two molecules of this thing. But I want to make sure when I draw those two molecules that I'm facing the groups that I'm going to be combining next to each other, because that's what's going to make sense. Okay, so this is how I did it. This. I did it in skeletal. So this is what I did. See if you can track along. Because I was like, this is gross. And I'm going to do this. That was my first. Do you agree with this?
Yes.
For that thing? That that's that?
Just.
That is that? Okay. Then I do it again. But this time, instead of these two groups like this, because it's a single bond, I rotate them around. Because I want the COOH of one to face the NH2 of another. So I drew my second one like this. H and H, just so I can see what's going on. The NH2. And then after that, I drew gross. And then I drew this. So like, we'll draw. Yes. Yeah. So how do I put this together? What do I have to take out to make the condensation polymer? I have to take out water, right? I have to take out water from here. And where else? Here. One of those. And where else? There. Okay, so how do I put that into a product? Where would we start? I would probably rotate here. Like I would rotate this. And I would rewrite this one starting at the nitrogen. So I would write nitrogen. I would write a little hydrogen for myself. And I know I'm taking a hydrogen out. And then I would write my next part, which is this. That's that. Then I would do this. What am I connecting this to? I take out the water, the C double bond O. What comes next? The nitrogen. Then I would rotate this and put the COOH on the outside because rotation is free around a single bond. So I would write that. I would write that. And then I would write this. And I believe if I double check, yeah, that's the answer. And this. So that's where it gets a little bit complicated. And that's why I said for me, I have to usually write everything out to understand what's going on. Because you have to understand that you can rotate the bonds. Now, if I had instead prepared this a little bit better and put my NH2 on the outside and this group on the top, I think it might have been a little bit easier. But this is a scenario you're going to come up in your homework. That is going to be like, how do I fix this? How do I rotate this? And you have to remember that the free rotation around single bonds. Which means that any of these groups could be on any of the sides. Meaning I could take the NH2, put it there, that, put it up there, the COH, put it up there. Like you can rotate those all around because there's free rotation around single bonds. There's no free rotation around double bonds. And so that kind of helps you to visualize how you're going to manipulate equations. How many marks is this word? 2. And look at the next one. Why do condensation polymers biodegrade? And this is recent, so this is how it's tested right now. That more readily than addition polymers. Isa, go ahead. Because they can be hydrolyzed is the exact answer. So because they can be hydrolyzed, that bond can be broken, which means they are susceptible, especially to acids and bases. And that's it. We have done lesson 1, which was a big lesson on polymers, a revisitation of the topic of polymers. This homework is due on Tuesday. Tuesday.
We're doing the better giver.
Sophia, Stefan, thank you so much for your help.
Better.
And you are adopted to the
Like,
class.
just get to choose it by yourself. And like, that's like, ask them.
And you're also
You
some
can
of the-
literally talk about math. Like, it has to be yes or no question. Like, still.
Not Sophia,
You know,
that's
like,
right.
should mathematics be
You're
like,
here for
you
a
know,
reason.
like, yeah, you can like do that.
No, it ain't about
Yeah, then you can use sources. Yeah,
I mean, like, not,
can't do that.
not all your classes, like, you know, keep it up. Just to be fair.
Like, should higher level mathematics be like principal study in you know,
All things considered.
Is your global presentation?
no. I was just like kind of like,
Okay.
yeah.
All
I
things
think
considered.
finally, maybe.
Seems doable,
Seems doable so far?
but that's also the first lesson.
Pretty simple-ish, right, Daniel? Pretty simple-ish, you know.
So like this type of topic, because I mean.
Thank you, Daniel, for locking in. Now I can maybe get a big one later. Perhaps. Yeah, eventually. I go get my ultra deluxe.
Z is more hydrophilic because it's cold. So there's ideas in there that are like from AS chemistry. That's what I was mentioning earlier. Yes.
Should I do it? Should I take media studies or should I do so it's easier?
I guess Miss Ledesma liked our lesson.
This was
She wrote, she put that. You're allowed to read.
like. Okay, here.
He's not here. Sorry. Okay. Chelsea.
No, from Ledesma. Should I do?
Oh, we're doing media studies or what?
You guys got your papers.
Okay.
Like, what do you?
I think, you know, it's up to you. Do you want those ACE exams? First of all. Do you want those extra ACE exams?
I want like the colleges to see them still doing like.
How many ACE classes do you have right now? Well, like ACE Bio says that I work hard. Like ACE Bio, like just ACE Bio says I work hard. I would say you're in your senior year. Take it a little easier. You would be excellent at taking pictures around the school.
You're so yeah.
And then as you know, science aid, you can also take pictures when the class is doing. I'm just saying,
You're right.
Miss Bleed's perspective is to do that.
Yeah.
Yes, ma'am.
So for this one,
Yeah.
I understood basically all of it except when you took.
When you have to flip them.
No, when you took the
Hey, I already did a.
and then when you split it out because I don't.
You have it here.
I know because I copied it off the board, but I mean like. How did you know what to add it to? Because I would have just been like, well,
For this one,
yeah, because I
it's
would
to
have
add
just
it to
broken it up
itself.
from here.
it's to add. It adds to itself.
Okay.
Is the idea. So you have to write it 2 times.
Okay, so if it doesn't
Equals
directly tell
right
you,
2 times. Because for condensation polymers, you have to have 2, but that's only 1. So you have to write.
because when I started doing it on my own, I was doing it with the own. So I was like, oh, I have to take the water from these 2
you
things.
gotta write it twice.
And so I was
I
like
get where,
doing it, but I
but
wasn't.
you needed 2.
Okay,
You
okay.
have to have 2.
Okay, so.
Chelsea, any
it
other
doesn't say
questions?
I have to-
To change our thing of our MOFs thing, because remember we were thinking like a patch or a.
Yes.
I saw something that said like a nasal spray, because that way it gets past the blood-brain barrier. So I think that's the best thing to do, like a nasal spray. And I was trying to like ask more questions about it to like Gemini, and then it's like this conversation is becoming unsafe. I'm like, what? And it keeps like not answering.
Repeat again to me.
About like I was saying that I found out that like an intranasal spray is like the best way to do the MOFs thing because it gets
Okay.
past the blood-brain barrier that way. But that Gemini keep like
Thursday.
asking.
Are you gonna be here after school on Thursday?
Yes. What's happening?
Sound.
Like right after school, 2:30?
Yeah.
Let me see if I can feed it to ChatGPT with my ChatGPT Plus subscription. See if ChatGPT will
It's unsafe.
Okay, so back off Gemini because they're gonna like report you too. No, they won't. I'm just saying.
Oh my god, I've like re-asked it like 400 times.
Pastoral counts. Recruit a pastoral count.
I keep like, oh my
No,
god.
no, don't stress it. But I'm just saying, let's try a different pathway, and I will go to ChatGPT and see what they say.
Okay.
But look, Chelsea, this is what Miss Ledesma said.
Yeah, that's how she knew. Like she knew once you said that the class average on this was like 100 too.
But I had written this
Yeah,
out
she was
like this morning. I was like,
Let me just
wait a second. You know, I was gonna say this was Ledesma's here to watch for like our formal observation, given for the formal observation.
Oh, that's what it was.
Yeah, that's what it was. Every teacher said, and I was like, you know what? I'm just gonna say it anyways. 'Cause I was planning to say it, and they always say not to like change what you're doing. So I was like, you know what? It's fine. I'll just say it. I'm gonna try not to get emotional, but like maybe I might have been more emotional if she wasn't here. Like I'm like, don't get I was like, I'm gonna hold it together. I'm gonna try to put it together.
It was good. That was good.
I
Especially
have more stuff to say, but I was like, thank God I wrote it down because I was like, because I was thinking about it last night and this morning. I was like, you know what, I need to write this down because otherwise I'm just gonna like go into a random tangent. But I felt like you all needed to hear it, and I'm not always very vocal about it, but I'm like, you all are so amazing. You should know that you're also amazing. So I just wanted you all to recognize the incredible achievements you have had and continue to have.
Miss, I have a question. I'm sorry. I have to ask. About previous students. Okay, I was looking. MDC has basically no chemistry classes. I mean,
Nothing more advanced than what you're doing. I mean, Orgo 1 and Orgo 2.
Yeah, but I have a full year there.
Yeah? My advice would be take 1046 Orgo 1, Orgo 2 because you'll still get more information. Like there's some stuff that's in there that would be like on the Olympiad that's not in the Cambridge curriculum. Just FYI. Yes. Luke missed like all the important stuff. No. He missed all the important stuff.